A silent city of galaxies floats over 300 million light-years from Earth. This is the Leo cluster, an immense gathering of stars and secrets that defies our understanding at every turn. By the end of this journey, you will have explored 25 of its most profound and unexplained cosmic mysteries. We will confront a black hole that should not exist and a galaxy made almost entirely of shadow. What strange force carved a billion light-year void into the fabric of the cluster itself? The answers we seek are not just about distant lights, they are about the fundamental rules of reality. What does it feel like to stand at the edge of a mystery this vast? Our first mystery is a cosmic absence so vast it feels like a scream in the silence. Deep within the bustling Leo cluster, astronomers found a place where almost nothing exists. They call it the Fornax Void. Picture a bubble in the universe, a spherical region of space spanning hundreds of millions of light-years. Inside, the normal rules of the cosmos seem to have been forgotten. Where we expect to see thousands of galaxies glittering like cities in the night, we find only a handful scattered and lonely. This is not a small gap. It is a staggering emptiness on a scale that our best models of the universe struggle to explain. How does a structure as massive as the Leo cluster, a place of immense gravitational pull, contain a hollow of this magnitude? The standard story of cosmic evolution says matter should clump together over time, drawn by gravity into filaments and walls with voids forming between them. But the Fornax Void is not between the walls. It is a gaping hole punched directly into one of the walls itself. It is as if you found a perfectly spherical room, 1,000 miles wide, hollowed out inside a mountain. The mountain should have collapsed into that empty space, but it hasn't. So what is holding the mountain up? One unsettling theory suggests the void is not empty at all. It may be filled to the brim with the universe's most elusive ingredient, dark matter. In this view, the void is a dense reservoir of this invisible mass, its gravity so strong that it actually pushed the normal, luminous galaxies out, creating the illusion of a desert. We are essentially looking at a ghost, a shape defined by what it has removed. Another, even more radical idea is that the void is a relic of the universe's earliest moments, a fossilized bubble from a time before stars, a primordial defect in the fabric of space that never filled in. Each explanation is stranger than the last. The Fornax Void asks us a profound question. Is the true architecture of the cosmos built from the light we see, or from the dark, unseen scaffolds in between? This impossible black hole lies at the center of a galaxy named NGC 3842. The galaxy itself is not the largest in the Leo cluster. It is a massive elliptical galaxy, but it fits within the expected hierarchy. Its central black hole, however, does not. When astronomers finally managed to weigh it, the numbers were staggering. This cosmic monster tips the scales at nearly 10 billion times the mass of our Sun. To grasp that scale, picture our entire solar system, from the Sun to the distant cloud of comets that surrounds it. Now imagine an object so dense and powerful that its gravitational influence would swallow that entire system whole, and then multiply that by 10 billion. That is the sheer immensity we are discussing, and that is the problem. According to our best models of how galaxies and their black holes evolve together, a galaxy the size of NGC 3842 should host a black hole perhaps 1/10 that mass, maybe even less. This is not a slight discrepancy. It is a fundamental challenge to the story we have written about cosmic growth. We thought we understood the partnership. A galaxy and its central black hole grow in lockstep, feeding on gas and sometimes merging with other galaxies over billions of years. The black hole's mass is supposed to be a reliable reflection of the galaxy's central bulge of stars. But here, the black hole is like a toddler who weighs as much as a professional athlete. The body does not match the strength, so how did this happen? One possibility is that this black hole is a primordial giant, a relic from the universe's chaotic infancy. It may have formed directly from the collapse of a gigantic cloud of primordial gas, bypassing the slower growth stages entirely, becoming a behemoth before its galaxy even finished taking shape. Another, more dynamic idea involves a history of rampant feasting. Perhaps NGC 3842 was once the dominant galaxy in a colossal merger, devouring several other large galaxies and funneling their black holes into its core, where they coalesced into this single, unimaginably dense object. The evidence for such a violent past might be written in the motions of stars far from the center, subtle clues of a gravitational upheaval that has since settled. But the most profound implication is this: if black holes can grow this large, this fast, then our timeline for cosmic structure is wrong. The universe might have built its most terrifying objects far more efficiently than we ever dreamed. The monster in NGC 3842 is not just an outlier, it is a question mark carved into the heart of a galaxy, asking us how well we truly understand the appetites of the dark. The monster black hole is a gravitational tyrant, but the Leo cluster holds structures of breathtaking subtlety as well. Wrapped around the massive galaxies M105 and NGC 3384 is a cosmic phantom, a faint, perfect loop of hydrogen gas and newborn stars. They call it the Leo ring. This is not a ring like Saturn's, a tight band of ice and rock. This ring is a cosmic structure over 650,000 light-years across, so vast it could contain our entire Milky Way galaxy with room to spare. For decades after its discovery, it appeared only as a wispy circle of cold hydrogen, a ghostly outline against the dark. Then, newer observations revealed a stunning secret. Scattered along its length are pockets of brilliant blue, clusters of young stars blazing to life. This ring is not just a relic, it is a stellar nursery, a place where the universe is actively building. But how did such a pristine, star-forming ring form in the first place? The leading theory is a story of cosmic violence. Imagine two massive galaxies, like M105 and its neighbor, passing through or near each other billions of years ago. Their gravitational fields would have interacted like stones thrown into a pond, sending immense ripples through the vast clouds of gas that surrounded them. One of those ripples could have been flung outward, a wave of gas shocked and compressed into this perfect circle, left behind to slowly coalesce into the ring we see today. This is the collisional ring theory, and it paints a picture of a dramatic ancient encounter. The problem is the ring's startling purity. The gas in the Leo ring is remarkably clean, almost devoid of the heavier elements, what astronomers call metals, that are forged in stars and scattered by supernova. If this ring was torn from the guts of massive, evolved galaxies, it should be contaminated with those metals. Its pristine nature suggests it might be something far more primordial. This leads to the alternative hypothesis. What if the Leo ring is not debris from a collision, but a fossil from the birth of the cluster itself? In this scenario, the ring is a leftover filament of the primordial gas that filled the universe after the Big Bang, a thread of pure hydrogen and helium that never fully collapsed into a galaxy. It simply hung there for billions of years, a sleeping giant of potential, until some recent disturbance, perhaps the gentle tidal pull of the nearby galaxies, finally triggered it to awaken and begin forming its first generation of stars. This makes it a living relic, a direct window into the raw material of the early cosmos. So we are left with a beautiful contradiction. Is the ring the scar of a terrible crash, or is it a preserved fragment of cosmic dawn? Its very existence challenges our ideas about how gas behaves over eons. It shows us that the universe can craft objects of immense scale and delicate beauty, whose origins remain whispered in the light of their newborn stars. The delicate ring shows us one face of the unseen, but dark matter wears many masks. In the galaxies M96 and NGC 3379, it takes on a form that is deeply puzzling. These two galaxies, a spiral and an elliptical, should be very different in their structure and history, yet they share a secret: observations of how stars and gas move within them, along with subtle distortions of light from background objects, reveal the presence of immense halos of dark matter surrounding each galaxy. This is expected. The shock is in the shape. According to the prevailing cold dark matter model, these halos should be roughly spherical, like a diffuse cloud enveloping the luminous galaxy at its core. But the data from M96 and NGC 3379 tells a different story. Their dark matter halos appear flattened, almost disk-like, and their density does not drop off with distance in the smooth, predictable way our models demand. It is as if we deduced the shape of an invisible animal by watching how it disturbs the grass around it, only to find its footprints suggest a creature with a form we have never seen before. This is not a minor detail. The properties of dark matter halos are a cornerstone of modern cosmology. They dictate how galaxies form, how they spin, and how they cluster together. If these halos in the Leo cluster are shaped wrong, it implies something fundamental is missing from our understanding. One possibility is that dark matter itself is more complex than we assumed. The cold dark matter model treats it as simple, slow-moving, and non-interacting particles that feel gravity and nothing else. But what if dark matter particles can interact with each other through some unknown force? This self-interaction could create friction, smoothing out the halos and shaping them into these flattened configurations, much like how a spinning ball of dough flattens into a disk. Another, more radical interpretation challenges the need for dark matter entirely. Theories like modified Newtonian dynamics, or MOND, propose that our understanding of gravity itself is incomplete on the scale of galaxies. In this view, the strange motions of stars are not due to invisible halos, but because gravity behaves differently when its pull becomes incredibly faint. The flattened halos could then be an artifact, a ghost in the data created by our insistence on using the wrong equations. Each galaxy, M96 with its spiral arms and NGC 3379 with its smooth glow, becomes a separate laboratory testing the same profound laws. Their agreement makes the mystery harder to dismiss. They are not screaming anomalies, but quiet, consistent whispers from the dark, suggesting that the universe's most abundant substance is either far stranger than we thought, or that we are standing at the edge of a rewrite of physics itself. The whispers of dark matter are subtle, but the Leo cluster also broadcasts its history in screams of raw energy. Between the galaxies of a subcluster known as Abell 1367, astronomers have mapped a colossal arc of radio light. This is not starlight, this is a ghostly afterimage, a fossilized shockwave frozen in space spanning over 1 million light-years. They call it a radio relic. To understand what we are seeing, you must listen with a different sense. The universe is filled with a sea of invisible particles, electrons, moving at nearly the speed of light. When these particles spiral through magnetic fields, they give off radio waves. The relic in Abell 1367 is a vast sheet where this process is happening on an almost unimaginable scale, painting a faint, structured halo in the darkness. The leading story is one of catastrophic violence. This relic is believed to be the aftermath of one of the most energetic events in the cosmos, the collision and merger of two entire galaxy clusters. Picture two of the largest gravitational structures in the universe, each containing hundreds of galaxies and vast oceans of hot gas, slamming into one another at millions of miles per hour. The collision would send a titanic shockwave racing through the intergalactic gas, a cosmic tsunami traveling at supersonic speeds. This shockwave acts like a natural particle accelerator, more powerful than any machine on Earth, compressing magnetic fields and flinging electrons to relativistic velocities. The relic is the glowing scar left by that passing wave, a billion-year-old echo of the crash. Yet for all the elegance of this story, the details defy us. The relic's brightness and its sharp, defined structure are puzzles. The shock wave from a merger should be more diffuse, a fading ripple. This arc is bright and coherent, like a neon sign in the void. Where is the precise source of the ongoing energy that keeps it so vivid? The merger event itself happened long ago, so the shock should have dissipated. Something must be continuously re-energizing the particles within it, or we are seeing it at a very special, fleeting moment in time. Furthermore, the exact mechanism that accelerates the electrons to such fantastic speeds within the shock is not fully understood. It is a natural process far more efficient than our theories often predict. Is there turbulence within the shock, a chaotic churning that acts like a cosmic pinball machine, bouncing particles to ever higher energies? Or does the relic trace something even rarer, like the wake of a truly immense galaxy plowing through the cluster gas at extraordinary velocity? This luminous arc is more than a remnant. It is a cosmic fossil that still glows with the heat of creation, a permanent record of a violence so vast it shaped the landscape of the cluster. By studying its faint radio whisper, we are not just looking at a past explosion. We are trying to decipher the physics of invisible forces operating at the very edge of reality, where the universe itself becomes the ultimate laboratory. The radio relic glows with the memory of ancient violence, but some secrets in the cosmos are defined by their profound silence. Drifting in the outskirts of the Leo cluster, in the neighboring region of Coma Berenices, there is a galaxy that should not be. Its name is Dragonfly 44. To our telescopes, it is little more than a faint, wispy smudge, a ghost of a galaxy so diffuse that it was only discovered with special, ultra-sensitive lenses. Yet this ghost holds a terrifying weight. Dragonfly 44 is as massive as our own Milky Way galaxy. It contains roughly the same amount of total matter, enough to birth hundreds of billions of stars. But here is the impossible part. It emits only 1% of the light a galaxy of that mass should. Where the Milky Way is a brilliant spiral of starlight, Dragonfly 44 is a vast dark shadow. The numbers are staggering. Follow the logic. We can measure the galaxy's mass by observing how fast its few visible stars move. Their high orbital speeds tell us something immensely heavy is holding them in place. When astronomers did the math, they found that over 99.99% of that mass must be dark matter. This is not a galaxy with a dark matter halo. This is a dark matter halo that has, almost as an afterthought, managed to collect a tiny sprinkling of stars. It is a cosmic skeleton, the invisible gravitational framework of a galaxy, laid bare for us to see with almost no flesh of stars upon it. So what happened here? Why did this galaxy, endowed with the same raw material as our own, fail to light up the darkness? The leading theory points to a tragic birth. In the dense, chaotic environment of the early cluster, Dragonfly 44 may have formed in a region where the gas clouds were stretched thin and stirred by violent tidal forces. The process of star formation is a delicate one. It requires gas to cool, condense, and collapse under its own gravity. If the gas is too hot, too turbulent, or too diffuse, that process never properly ignites. Imagine trying to start a campfire in a strong, gusty wind. The fuel is there, the matches are there, but the flame never catches and grows. That may be the story of Dragonfly 44. It had all the fuel, but the environment was too hostile for the fire of star birth to take hold. Another possibility is even more haunting. Perhaps the galaxy did form stars initially, but some catastrophic event, like a near collision with a much larger neighbor, ripped away its gas and quenched its stellar nurseries long ago, leaving behind only this dark, star-poor remnant. It is a galactic ghost story. Dragonfly 44 forces us to ask a fundamental question about the universe. Is the glorious spiral of the Milky Way the rule, or is it the exception? What if, for every brilliant galaxy we see, there are dozens of these dark, failed giants floating unseen in the void? this phantom galaxy suggests that dark matter is not just an ingredient in the cosmic recipe. In some places, it is the entire meal, and the stars are merely a forgotten garnish. A galaxy made of shadow is a monument to cosmic silence, but the Leo cluster also broadcasts in sudden, deafening shouts. In 2019, a telescope detected a series of powerful, fleeting blasts of radio energy that seemed to come from the general direction of this distant city of galaxies. This was not just another fast radio burst, it was a repeater. Most of these cosmic flashes are one-off events, a single, brilliant millisecond pop of radio waves from across the universe. This source, however, fired again and again. Each burst was unimaginably powerful, releasing in less than the blink of an eye as much energy as our sun emits over several days. To have that kind of raw power repeat from the same spot is a mystery that cuts to the heart of modern astrophysics. The leading suspect for such explosions is a type of stellar corpse called a magnetar. Imagine a neutron star, the collapsed core of a giant star, crushed into a sphere just a dozen miles across but weighing more than our sun. Now spin it up and wrap it in a magnetic field 1,000 trillion times stronger than Earth. This is a magnetar, a cosmic powerhouse where the crust can crack under magnetic strain, releasing titanic flares. A single, catastrophic starquake on such an object could explain a one-time burst. But a repeater, that suggests the object is not just cracking, it is somehow reloading and firing over and over again, like a cosmic gun with an endless magazine. The fact that this repeater's likely home is in the Leo cluster adds another layer of intrigue. This places the source in a dense, ancient environment, a place full of old stars and the remnants of stellar lives. Could the bursts be coming from a magnetar orbiting in a peculiar binary system, where interactions with a companion star periodically trigger the eruptions? Or is the source something even more exotic, like a pulsar plunging through a dense asteroid belt, with each collision creating a radio bang? The distance itself is a key part of the puzzle. Fast radio bursts are used as cosmic yardsticks. Their signals are dispersed by the thin gas between galaxies, and that dispersion tells us how far they have traveled. A repeater from the Leo cluster has traveled over 300 million light-years. For a signal to remain coherent and powerful enough for us to detect after such an epic journey, the engine behind it must be almost unthinkably efficient. This is not a local event. It is a message in a bottle hurled across an ocean of time and space, and the bottle keeps getting thrown. Each repeating burst is a clue, but also a contradiction. They rule out cataclysmic, one-time events like the collision of two neutron stars, which would destroy the source. Instead, they point to an object that survives its own ferocious outbursts, a durable cosmic lighthouse flashing its beam toward Earth with a rhythm we cannot yet predict or comprehend. In the silent halls of the Leo cluster, something is not just whispering, it is screaming over and over, and we are only just beginning to hear it. While the repeater screams across the void, the Leo cluster also bears scars of a slower, more majestic violence. One of its most famous residents, the elegant spiral galaxy NGC 3628, wears its history like a banner of light. Stretching away from its disk is a breathtaking structure, a river of stars and gas over 300,000 light-years long. This is a tidal tale, a cosmic brushstroke painted by gravity itself. It formed when NGC 3628 had a close encounter with another galaxy, its immense gravitational pull stretching and tearing material from the spiral's outer regions, flinging it into intergalactic space. The result is a luminous trail, a literal piece of the galaxy ripped away and set adrift. For a long time, the story seemed simple. One galactic pass, one graceful tale. But the devil, as always, is in the details. When astronomers looked closer at this titanic stream, they found its story was not a simple parable, but a complex epic. The kinematics, the precise motions of the stars and gas within the tail, are chaotic. They do not follow the smooth, predictable flow you would expect from a single, clean gravitational pull. Instead, the material seems to churn and clump in unexpected ways. Even more telling are the star clusters embedded within the river of debris. These are not just random sprinkles of old stars dragged from their home. Scattered along the tail's length are pockets of brilliant blue, indicating surprisingly young, massive star clusters. This is a crucial clue. Star formation is a process that requires dense, cool clouds of gas to collapse. The violent act of having your galactic arm ripped off is not typically a gentle, nurturing environment for stellar birth. It is a disruptive, heating event. The presence of these young clusters suggests the tidal tail is not a simple, one-time event that then faded into darkness. It implies that within this flung-out debris, pockets of gas were able to shock, compress, and collapse, igniting new fires even as they were exiled from their parent galaxy. This forces a dramatic reinterpretation of NGC 3628's past. That close encounter may not have been a simple flyby. It could have been a far more intimate and prolonged dance, perhaps even a full merger with a smaller companion galaxy. The gravitational turbulence of a merger would churn the gas much more violently, creating the dense knots necessary to trigger starlight in the midst of chaos. The tail, then, is not just a wound, it is a stellar nursery born from catastrophe, a place where destruction and creation are two sides of the same cosmic coin. This magnificent stream of light is more than a beautiful accident. It is a forensic snapshot, a billion-year-old crime scene where the motions of stars and the birth of new suns are rewriting the history of a galactic encounter we thought we understood. The tidal tail shows creation sparked by chaos, but another galaxy in the cluster demonstrates a far more chilling form of control. NGC 1125 appears as a quiet, red, and dead elliptical galaxy, its days of star formation long over. Yet deep within its core, a hidden monster is not just sleeping, it is actively enforcing the silence. Astronomers classify this galaxy as a red geyser. The name is perfectly apt. A geyser on Earth is a vent that periodically erupts, shooting hot water and steam into the air. In NGC 1125, the supermassive black hole at its center acts in a similar way. It does not feast in a brilliant, visible quasar outburst. Instead, it feeds in fits and starts, and with each small meal, it unleashes a powerful wind of superheated gas and magnetic energy. These winds blast outward through the galaxy at millions of miles per hour, scouring the interstellar medium. They are the ultimate cosmic regulators. For stars to form, giant clouds of cold gas must collapse under their own gravity. The black hole's winds act like a cosmic blowtorch, keeping that gas hot, turbulent, and diffused. It constantly stirs the pot, preventing the ingredients from ever settling down to create new stellar fires. The galaxy is not just old and red, it is being kept red, its star-forming potential systematically quenched by an unseen hand. This leads to the central mystery. In a typical quasar, the furious feeding of a supermassive black hole creates an accretion disk of glowing, infalling gas so bright it can outshine the entire surrounding galaxy. We see a brilliant beacon at the core, but in NGC 1125, the quasar is hidden. Our optical and ultraviolet telescopes see no such brilliant beacon. The black hole is clearly active, its winds are proof, yet the light from its feast is strangely absent. Where is the glow? One compelling answer is that we are looking at it from the wrong angle or through a cosmic veil. The black hole could be surrounded by a thick, donut-shaped ring of gas and dust, a structure astronomers call a torus. If we are viewing the galaxy from the side, looking through the dense wall of this torus, it would completely obscure the brilliant accretion disk at the center. We would not see the dazzling quasar light, but we would still feel the effects of its powerful winds blowing out through the top and bottom of the donut. Another possibility is even more intriguing. This may represent a distinct low-energy state of black hole feedback. Perhaps the black hole is feeding on a sparse, trickling diet of gas, just enough to power these fierce winds, but not enough to ignite the sustained, dazzling brilliance of a full quasar. It is a maintenance mode, a steady drip of energy that is perfectly calibrated to suppress star formation without the theatrical flare. This red geyser presents a profound cosmic irony. The most energetic object in the galaxy, the supermassive black hole, has used its power not to illuminate but to darken. It has not sparked creation, it has enforced a permanent autumn, ensuring that no new stars will ever rise to challenge its quiet, chilling dominion over the galactic landscape. The red geyser enforces a quiet death, but the space between galaxies in the Leo cluster is not entirely dark. There is a ghostly luminescence there, a faint, pervasive glow that bathes the entire core in a soft, ethereal light. This is intracluster light, and it comes from stars that are no longer citizens of any single galaxy. These are orphan stars, billions upon billions of them, cast adrift into the immense gravitational sea of the cluster itself. They form a diffuse cosmic fog, a background shimmer that has been stripped from their galactic homes. In the Leo cluster, however, this fog is not just present. It is blindingly bright, far more intense than our models of cluster evolution can comfortably explain. The sheer volume of this free-floating starlight tells a story of almost unimaginable violence. Think of it like this: a galaxy is a vast city of stars held together by its own gravity. For stars to be ripped from their city and tossed into the intergalactic wilderness, something truly catastrophic must happen. Gentle interactions will not do it. It requires the gravitational equivalent of a demolition derby. The leading theory involves a history of relentless galactic cannibalism. The Leo cluster's core is dominated by a few monstrous elliptical galaxies, like M105. These giants are thought to have grown to their immense size by devouring smaller satellite galaxies over billions of years. When a small galaxy falls into a larger one, it doesn't just get swallowed whole like a marble. The process is far more messy and destructive. The immense tidal forces, the difference in gravity between the near side and far side of the smaller galaxy, act like a cosmic hand pulling it apart. Stars are yanked from their orbits and flung in all directions, some captured by the larger galaxy, but many others ejected entirely, becoming permanent residents of the intracluster space. The Leo cluster's anomalously bright glow suggests this process was not just occasional. It was a frenzy. It points to an epoch where the core of the cluster was a chaotic battlefield, a dense swarm of galaxies constantly smashing, grazing, and tearing each other apart. The intracluster light is the lingering dust from that cosmic war, the stellar debris that never settled. But the mystery deepens when we look at where this light is concentrated. It isn't a uniform fog. Recent observations show it is clumpy, gathered into faint streams and clouds that trace the gravitational skeletons of the cluster. These are the fossilized streams of devoured galaxies, their final shapes preserved in the glow of their exiled stars. This clumpiness is another clue that the stripping was not a single ancient event, but an ongoing, layered process. Some of these stellar streams may be relatively fresh, the remains of a galaxy that was torn apart only a few 100 million years ago, a blink in cosmic time. So the question becomes not just how so many stars were freed, but why the Leo cluster was such an efficient destroyer of galaxies. Was its core simply denser from the start, packing galaxies so close together that collisions were inevitable? Or did some earlier cataclysmic event, like the merger of two subclusters, stir the entire system into a violent frenzy, accelerating the cannibalism? This faint, pervasive glow is more than just lost light. It is a forensic archive. By mapping its subtle contours and measuring its brilliance, we are reading the violent autobiography of the cluster, written in the scattered stars of its countless victims. The ghostly light of orphaned stars tells a story of giants devouring the small. But one of the smallest members of the Leo cluster holds a secret that turns this entire hierarchy on its head. Drifting as a faint satellite near the massive galaxy M105 is Leo the First, a dwarf spheroidal galaxy. To the eye, it is unremarkable, a sparse, ancient collection of a few tens of millions of stars, a cosmic village compared to the Milky Way's sprawling metropolis. For decades, it was considered a quiet backwater, a simple fossil from the early universe. Then, astronomers decided to measure the motions of its stars with unprecedented precision. What they found was not the gentle drift of an old, relaxed system. The stars near the galaxy's core were whipping around at velocities so high they could only be held in place by a gravitational anchor of terrifying density. The math was inescapable. Hidden at the heart of this tiny, faint dwarf galaxy is a supermassive black hole with a mass approaching 3 million times that of our Sun. This is a monster of a scale we associate with galaxies 1,000 times larger. To grasp the absurdity, picture a small, quiet pond. You expect to find minnows and tadpoles in its depths. Instead, you drop a line and discover a creature the size of a blue whale lurking in the mud below. The sheer disproportion is what shatters our understanding. The established rule of galactic evolution is one of proportionality. A galaxy's central black hole mass typically correlates with the mass of its central bulge of stars. Large galaxies host large black holes, small galaxies host small black holes, or often none at all. Leo the First has virtually no central bulge to speak of, yet it possesses a black hole nearly as massive as the one at the center of our own vast Milky Way. This is not just an outlier, it is a direct challenge to the fundamental narrative of co-evolution. How does a galaxy with so few stars and so little visible structure come to harbor such a behemoth? One radical theory suggests Leo the First is not what it seems. Perhaps it is not a primordial dwarf galaxy at all, but the stripped remnant of a much larger galaxy that ventured too close to the colossal M105 long ago. In this scenario, Leo the First was once a respectable spiral, but the tidal forces of its giant neighbor ripped away over 99% of its stars and gas, leaving behind only its dense, star-poor core and the monstrous black hole that once governed it. It is a galactic ghost, a shadow of its former self, with its hidden heart betraying its glorious past. Another, even more profound idea is that this black hole formed first. In the primordial universe, gigantic clouds of pure hydrogen and helium may have collapsed directly into massive black holes, bypassing the star formation stage entirely. These black hole seeds would then act as gravitational anchors around which galaxies slowly assembled. Leo the First, in this view, might be a failed galaxy, a place where the seed was planted but the full structure never grew, leaving the black hole as a relic of that aborted process. The implications ripple outward. If tiny Leo the First hides such a giant, how many other faint dwarfs drifting in the darkness of the Leo cluster and beyond are secretly harboring similar monsters? Our senses of supermassive black holes and our entire understanding of how they shape their cosmic homes may be built on a foundation that has missed the most shocking residents of all. The silence of this dwarf galaxy is a deception, and its stillness masks the gravitational roar of an impossible king. The impossible black hole in Leo the First whispers of a violent past, but the very air of the Leo cluster tells its own, more pervasive story. Between the galaxies, in what seems like empty space, there is a thin, searing atmosphere. This is the intracluster medium, a vast ocean of gas heated to millions of degrees, so hot it glows not in visible light but in powerful X-rays. For decades, astronomers viewed this coronal gas as a simple byproduct of the cluster's formation, a uniform soup of hydrogen and helium cooked by gravitational collapse. Then they read its spectral signature, the unique chemical fingerprint imprinted on the X-ray light. The data revealed a shocking truth. This superheated plasma is not pristine. It is heavily polluted with the forged remains of dead stars, elements like iron, oxygen, silicon, and neon. The sheer abundance of these metals, particularly iron, is staggering. To enrich an ocean this vast, spanning millions of light years, would require the coordinated effort of trillions upon trillions of supernovae, the catastrophic explosions of massive stars over billions of years. The gas is essentially a cosmic junkyard filled with the scattered ashes of countless stellar furnaces, but the distribution of these elements is the real puzzle. The iron, for example, is not clumped tightly around the giant galaxies where most of the stars, and therefore most of the supernova, would have occurred. Instead, it is spread with surprising smoothness throughout the entire intracluster volume. This evenness defies a simple story. If supernova alone were responsible, their explosive feedback should have created a messy, lumpy enrichment pattern with dense pockets of iron near the big galaxies and far poorer regions in the voids between them. The observed smoothness suggests something stirred this cosmic pot with incredible efficiency, mixing the stellar ashes into a homogeneous blend. What force could possibly achieve this? The leading suspect is the same violence that created the intracluster light and the radio relic, a history of colossal mergers. When entire subclusters of galaxies collided, the resulting shockwaves would have raced through the gas, not just heating it but churning it like a titanic whirlpool. These mergers could have acted as a galaxy-scale blender, thoroughly mixing the enriched material ejected from hundreds of galaxies over eons. Yet, even this dramatic explanation hits a snag when we look at specific ratios. The amount of oxygen compared to iron is also a clue. Different types of supernova produce these elements in different proportions. The classic core collapse supernova from a short-lived massive star produces lots of oxygen and other lighter elements. The thermonuclear explosion of a white dwarf star, a Type 1 supernova, is a primary factory for iron. The chemical mix in the Leo cluster's gas seems to require a specific and incredibly productive sequence of both kinds of explosions, fine-tuned over the cluster's entire lifetime. This forces astronomers to reconsider the very engines of galactic feedback. Were the ancient galaxies in the Leo cluster far more efficient at expelling their manufactured elements than any galaxy we see nearby? Did they possess a form of supernova-driven wind so powerful it could fling heavy metals clear out of their galactic boundaries and into the cluster at large, seeding the void with the raw materials for future generations of stars and planets? The coronal gas is a fossilized record of the cluster's chemical evolution. Its unexplained chemistry is a message in a bottle written in the language of atomic nuclei, telling us that the life and death of stars in this dense environment did not just shape galaxies, it fundamentally poisoned the entire ecosystem they float within. The chemical history of the cluster is written in its hot gas, but the personal history of a single galaxy can be read in the motion of its stars. At the heart of the spiral galaxy NGC 3607, astronomers discovered a dizzying contradiction. The vast disk of the galaxy spins one way, a majestic whirlpool of billions of stars. Yet nestled at its very center, a dense core of stars spins just as rapidly in the exact opposite direction. It is as if you found a gigantic whirlpool in the ocean, and at its very eye, a smaller, perfect whirlpool was spinning the opposite way, defying the flow that surrounds it. This is a counter-rotating core, a clear and violent signature of a past galactic merger. The story seems straightforward. Billions of years ago, NGC 3607 likely consumed a smaller satellite galaxy. This victim galaxy would have approached on a retrograde orbit, meaning it was swinging around the larger galaxy in the opposite direction to the main disk's rotation. As it was torn apart and swallowed, its stars, now stripped of their original home, would have settled into the central region, preserving their backward motion. They became a distinct population, a fossilized crowd spinning against the galactic grain. This narrative, however, raises more questions than it answers. The mystery is not that it happened, but how it happened with such surgical precision. Why is the counter-rotating core so sharply defined? The transition between the backward spinning core and the forward spinning main disk is not a gradual blend. It is a stark boundary. Imagine pouring cream into a swirling cup of coffee. Turbulence and diffusion would mix the two fluids, creating a blurred intermediate zone. Galactic dynamics should work the same way over cosmic time. The gravitational interactions between stars in the core and stars in the disk should have gradually erased this sharp divide, smearing the opposite rotations into a more homogeneous mix over a few billion years. Yet the core in NGC 3607 remains distinct, a separate engine running in reverse within the larger machine. This persistence suggests the core is not just a collection of captured stars, but a dynamically cold and incredibly stable structure. The stars within it must be moving on very ordered circular orbits, a configuration that is resistant to disruption. How did the merger process create such a pristine, ordered core from the chaos of a galactic collision? One possibility is that the swallowed satellite was not a typical, fluffy dwarf galaxy, but something far denser and more massive. Perhaps the compact core of a once larger galaxy that had already been stripped of its outer layers. This dense nugget would have sunk to the center of NGC 3607 with minimal disruption, its stars already on tight, stable orbits, allowing it to maintain its identity. Another, more subtle idea involves the role of the supermassive black hole that undoubtedly sits at the very center of this galactic dance. The black hole's immense gravity can act as a stabilizer, its presence helping to shepherd the counter-rotating stars into a stable, long-lived configuration, effectively fossilizing the merger remnant against the eroding forces of the larger disk. The core of NGC 3607 is therefore a cosmic clock that seems to have stopped. It records the exact moment of an ancient catastrophe, preserving the orbital signature of a doomed galaxy with a clarity that should have faded eons ago. This sharp boundary between spinning regimes is a silent challenge to our models of galactic digestion. It tells us that mergers are not always messy affairs that completely homogenize a galaxy. Sometimes they can leave behind a perfect spinning scar, a ghostly fingerprint at the heart of a giant, whose backward whirl holds the secret to a violence that was both catastrophic and strangely precise. The spinning scar in NGC 3607 is a fossil of a precise collision, but the gravity of the Leo cluster can also bend light itself into a cosmic magnifying glass. One particular lens, focusing the image of a distant galaxy far behind the cluster, is telling a story that simply does not balance. Gravitational lensing is a powerful tool, a direct probe of mass. When the immense gravity of the cluster warps the fabric of space-time, it acts like a flawed lens in a giant telescope, distorting and often multiplying the image of a background object. By carefully mapping the exact shape of that distortion, whether the background galaxy appears as a stretched arc or a perfect Einstein ring, astronomers can calculate the total mass of the cluster region causing the bend. It is cosmic accounting. You measure the light you see from the cluster's galaxies and hot gas. You add the expected contribution from dark matter based on models, and that sum should perfectly predict the lensing distortion you observe. In this specific Leo cluster lens, the books do not balance. The distortion of the background galaxy is slightly, yet definitively, off. It implies pockets of gravity that are stronger than they should be, mass concentrations that are not fully accounted for by the smooth distribution of dark matter we expect to envelop the cluster. Imagine trying to deduce the shape of an invisible object buried in sand by only looking at the contours of the sand's surface. You expect a gentle, smooth mound, but instead you see sharp, unexpected pits and peaks. That is what this lens reveals, an invisible landscape that is more complex and clumpy than our maps predict. What could these gravitational anomalies be? One compelling possibility is that they are subhalos, dense knots of dark matter that orbit within the larger dark matter halo of the cluster itself. According to the cold dark matter model, these subhalos should be abundant, the leftover cores of small galaxies that were devoured long ago, their stars stripped away but their dark matter hearts still intact. This lensing distortion could be the first direct, localized evidence of such a structure, a solitary dark matter clump revealed only by the way it twists a thread of light from across the universe. Another, more turbulent explanation involves the recent violence of the cluster's history. If the Leo cluster is still settling from a major merger, the dark matter distribution may not have had time to smooth out into the relaxed, predictable shape our models assume. The collision could have stirred the dark matter sea, creating waves and eddies of density, precisely the kind of substructure that would cause these subtle, additional lensing effects. The background galaxy's warped image is therefore a snapshot of chaos in the process of calming down. This single misbehaving lens forces a profound realization. Dark matter may not be a perfectly smooth, passive fog. It might have a rich and complex topography of its own, with mountains and valleys of density that trace a violent history we are only beginning to decipher. The light from that distant galaxy did not just pass through the cluster, it recorded a detailed fingerprint of the cluster's hidden skeleton, and the fingerprint shows details we are still learning how to read. The lensed galaxy reveals a hidden topography of dark matter, but the Leo cluster also contains islands of unexpected light, drifting in the immense, hot ocean of the intracluster medium, far from the shores of any major galaxy. Astronomers found a strange, brilliant smudge. They nicknamed it the blue blob. This object is not a galaxy. It is a compact, isolated cloud of intensely blue stars, a tiny cosmic oasis of youth in the middle of a vast, ancient desert. The color blue is the key. In astronomy, blue light is the signature of hot, massive, and therefore short-lived stars. Where you see a concentrated patch of blue, you are looking at a region of very recent, vigorous star formation, typically no more than a few tens of millions of years old. The profound mystery of the blue blob is its location. It is completely alone. There is no spiral arm it belongs to, no dwarf galaxy it anchors, no visible reservoir of cold gas from which these stars could have been born. It simply hangs in the searing emptiness between galaxies, a stellar bonfire lit in the middle of a superheated sea. How do you start a fire in a place with no fuel and no obvious spark? The first theory is one of galactic theft. The blue blob may be the luminous heart of a small galaxy that was completely torn apart. Imagine a dwarf spiral venturing too close to one of the cluster's giant elliptical galaxies. The immense tidal forces could have stripped away 99% of its stars and all of its gas, leaving behind only its densest star-forming core. This core, now orphaned, might have retained just enough of its own cold gas to ignite one final, glorious burst of star formation before fading into obscurity. In this scenario, the blue blob is a galactic ghost, the last brilliant breath of a system that no longer exists. The second theory is far more radical. It suggests the blob formed right where we see it, a true child of the intracluster medium. This idea hinges on a startling possibility that vast, cold clouds of hydrogen gas can somehow survive like floating icebergs within the million-degree plasma of the cluster. If such a cloud existed, and if it was dense enough, it could theoretically collapse under its own gravity and form stars. The process would be incredibly rare, as the ambient heat should evaporate any cold cloud almost instantly. But perhaps this particular cloud was especially massive, or it was shielded and compressed by a passing shockwave from an ancient merger, providing the trigger for collapse. This would be in situ star formation, a stellar nursery born from the raw, isolated material of intergalactic space itself. The implications of this second idea are profound. It would mean the building blocks for stars and planets are not confined to galaxies. They can coalesce in the deepest voids, creating isolated stellar systems that owe allegiance to no galactic empire. These would be true nomads of the cosmos, born free and destined to drift forever in the darkness between the great islands of light. Right now, the blue blob is a vibrant blue, but massive blue stars live fast and die young. In just a few tens of millions of years, they will explode as supernova, scattering their enriched remains into the surrounding hot gas. The blob will fade to red, then darkness, leaving behind perhaps a cluster of older, cooler stars and a swarm of planets, a silent testament to a fleeting, impossible fire. Its very existence asks us whether the emptiness of space is truly empty, or if it secretly nurtures sparks of creation in its darkest, most unexpected corners. The vibrant blue blob defies its lonely location, but a far more fundamental kind of absence haunts the entire Leo cluster. In a subcluster known as Abell 1314, astronomers have run into a cosmic accounting error so large it challenges our inventory of the universe itself. The problem centers on baryons, the familiar particles that make up everything you can see and touch every star, every planet, and every human being. Based on meticulous measurements of the cosmic microwave background, the afterglow of the Big Bang, we know precisely how much of this normal matter the universe should contain. It is a fixed percentage of the cosmos. When we add up all the baryons we can see in Abell 1314, in its brilliant galaxies and its glowing X-ray gas, the numbers come up short. A significant fraction, perhaps as much as 30 to 40%, is simply missing. This is not dark matter. This is the ordinary stuff of creation that has seemingly vanished from the ledger. Where did it go? The leading suspect is not a place of darkness, but one of faint, diffuse heat. Theorists believe the missing baryons are hiding in a vast cosmic web of filaments, threads of warm hot gas that stretch between galaxy clusters. This is the warm-hot intergalactic medium, a state of matter so tenuous and so hot, at hundreds of thousands of degrees, that it is almost invisible to our current telescopes. It emits a faint glow in the far ultraviolet and soft X-rays, a whisper of light that is incredibly difficult to detect against the background noise of the universe. Finding it in Abell 1314 is like trying to spot a thin, hot mist spread across an entire continent, using only a telescope that is best at seeing either brilliant cities or cold, dark forests. The cluster's immense gravity should be drawing in these intergalactic filaments, funneling this warm, hot gas into its core. If we could see it, it would likely appear as faint, wispy bridges connecting Abell 1314 to the larger structures of the cosmic web. Their absence from our tally suggests our maps of the universe are still crude, that we are only seeing the bright nodes and have missed the gossamer threads that connect them. This missing matter problem transforms Abell 1314 from just another cluster into a crucial test site. Its gravity acts as a natural lens, magnifying the light from distant quasars shining behind it. As that light travels through the cluster and any surrounding filaments, atoms in the warm hot gas will absorb specific wavelengths, imprinting a unique signature on the quasar's spectrum. It is the astronomical equivalent of finding a stained filter in front of a distant spotlight. The stain tells you what the filter is made of. Astronomers are now hunting for these subtle absorption lines, the fingerprints of oxygen and other elements in a million-degree state. Each tentative detection is a clue, a piece of the missing universe slowly being dragged into the light. Solving this puzzle is about more than balancing a cosmic budget. It is about understanding the complete life cycle of matter. These missing baryons are the reservoir from which galaxies form and into which they eventually bleed their enriched material. They are the circulatory system of the cosmos. If we cannot account for them in a place as massive and well-studied as the Leo cluster, then our story of how the universe structures itself is missing a fundamental chapter. The silence in the data from Abell 1314 is not empty. It is the sound of a hidden ocean waiting to be heard. The missing baryons are a ghost in the cosmic ledger, but some objects in the Leo cluster are impossible to miss, even as they defy classification. Orbiting the massive elliptical galaxy M59 is a cosmic paradox called M59CO. It appears in telescopes as a tiny, dense smudge of light, no larger than a typical globular cluster, a mere 200 light-years across. That is smaller than the distance from our Sun to its nearest stellar neighbors, yet within this minuscule volume it packs a staggering gravitational punch. Measurements of the motions of its stars reveal it contains the mass of a small galaxy, perhaps several 100 million times the mass of our Sun. This is an ultra-compact dwarf galaxy, an object so dense it bends the rules of what a galaxy can be. To grasp the absurdity, picture a city. A globular cluster is like a dense, ancient village packed with old stars but relatively lightweight. A dwarf galaxy is like a sprawling town with more mass spread over a much wider area. M59CO is a city with the population and economic power of New York, compressed into the physical footprint of a single skyscraper. The density is almost unimaginable. Stars within it must be whizzing past each other at incredible speeds, their orbits a frenetic dance in an impossibly crowded space. How does such an object come to exist? Astronomers are locked in a debate between two equally dramatic origin stories. The first is a tale of galactic cannibalism. M59CO may be the stripped, naked nucleus of a once proud dwarf galaxy that ventured too close to the giant M59. In this scenario, the smaller galaxy's outer layers of stars and gas were completely torn away by tidal forces, leaving behind only its incredibly dense star-packed core. This core, now orphaned, continues to orbit the giant as a compact fossil, its immense density a relic of its former, larger structure. It is a galactic heart ripped from its body and left to beat alone in the dark. The second story is more radical. It suggests M59CO formed this way from the beginning, a genuinely new class of object born in the unique pressure cooker of the cluster environment. In the dense, chaotic core of the young Leo cluster, vast clouds of gas may have collapsed under tremendous external pressure, bypassing the normal, more leisurely process of galaxy formation. This rapid, violent collapse could have forged these ultra-dense stellar systems directly, with no extended halo or disk ever forming. They would be cosmic hailstones condensed from the super-saturated atmosphere of the cluster itself. The evidence remains tantalizingly ambiguous. The stars within M59CO are old and metal-rich, suggesting a long, complex history of star formation that aligns with the stripped nucleus idea. Yet its isolation and precise properties do not perfectly match any known type of galactic core. It sits in a strange middle ground challenging our categories. This tiny, brilliant speck forces a fundamental question about the universe's diversity. Are galaxies and star clusters two distinct families, or is there a hidden continuum of objects bridging the gap? M59CO, in its fierce, compact glory, suggests that in the extreme environments of galaxy clusters, the universe can forge hybrids that blur every line we have drawn. It is a reminder that sometimes the most profound mysteries are not vast and diffuse, but terrifyingly, brilliantly small. The extreme density of an ultra-compact dwarf is a local mystery, but a far broader pattern of movement may be choreographing entire families of galaxies. Around the dominant giants of the Leo cluster, like M105, swarm smaller satellite galaxies. These are not just randomly scattered. A growing body of observations hints that many of these satellites are not moving on chaotic, independent paths. Instead, they appear to be dancing in a vast, coordinated plane, a thin disk-like structure where their orbits are synchronized. This is not what our standard model of cosmic structure predicts. According to the cold dark matter paradigm, satellites should be accumulated over time from all directions, pulled in by the giant galaxy's gravity. They should swarm like bees around a hive, with orbits tilted at every possible angle, a messy, three-dimensional cloud of motion. The suggestion of a preferred, rotating plane is like finding all those bees flying in a single, flat, orderly ring. If confirmed, this synchronized rotation poses a direct challenge to the story of how the largest galaxies assemble their entourages. One profound explanation reaches back to the very birth of the cluster. The universe is not a blank space where galaxies form in isolation. It begins as a web, a cosmic network of dark matter filaments along which gas flows. The leading theory for this synchronization is that these satellite galaxies are not captured strangers. They may be the surviving remnants of an ancient river of gas and dark matter, a primordial filament that fed the growth of the central giant billions of years ago. In this scenario, small galaxies formed first along this dense, flowing thread like beads on a string. As the filament funneled material into the central galaxy, the beads, the proto-satellites, were carried along with the flow, inheriting the filament's direction and spin. Over eons, the filament itself dissipated, but the satellites preserved that original, shared motion, continuing to orbit in the ghostly imprint of that vanished river. They are not a random swarm, but a fossilized stream, a galactic convoy still traveling in the lane they were born in. This idea elegantly links the large-scale structure of the cosmic web to the intimate dynamics of a single galaxy's neighborhood. It suggests that the architecture of the early universe can leave a lasting, dynamical signature, visible billions of years later in the synchronized whirl of ancient suns. Yet, this explanation is not without tension. The violent environment of a massive cluster like Leo is a gravitational battlefield, full of close encounters and tidal shocks that should, over time, disrupt such a delicate, planar arrangement. The very fact that we might still see this coordination means either the plane is incredibly stable, or its formation was more recent than we think. Could a more recent group infall, a small cluster of galaxies being swallowed whole, explain the pattern, or does the persistence of this plane hint at something about the nature of dark matter itself, perhaps that it can form stable, disk-like substructures that shepherd luminous satellites? Each satellite in this possible dance is a clue. By mapping their precise motions, astronomers are not just cataloging neighbors, they are attempting to read the faded blueprints from the universe's construction phase, searching for the lost rivers that once watered the giants of the cosmos. The synchronized dance of satellites speaks to ancient order, but the Leo cluster also hosts moments of pure, catastrophic chaos. In a seemingly ordinary spiral galaxy within its bounds, astronomers witnessed a brilliant supernova erupt, a stellar explosion briefly outshining its entire host. Such events are cosmic lighthouses, and scientists immediately raced to scour archival images of that exact spot, taken before the blast. Their goal was to identify the progenitor star, the massive sun whose dramatic death had just lit up the universe. The pre-explosion data revealed nothing. Where there should have been a brilliant, unstable giant star, there was only empty space, a profound and unsettling silence in the records. This was not a case of missing data or a blurry image. The Hubble Space Telescope and other observatories had looked directly at that location with enough sensitivity to easily detect the kind of massive, luminous stars known to end their lives as supernova. The progenitor had simply vanished from the story before the story even began. This absence forces a fundamental re-evaluation of how some stars die. One possibility is that the star was there, but it was fainter than we expected. Perhaps it was shrouded in a thick cocoon of dust, dimming its light so much that it slipped below the detection threshold of our telescopes. In this scenario, the star's own violent final acts, like casting off its outer layers, may have created the veil that hid it from our view. The supernova blast itself would then have blown that dust away, revealing the catastrophic aftermath but obscuring our view of the cause. Another, more intriguing line of thought challenges our classification of stellar deaths. We categorize supernovae into types based on the chemical fingerprints in their light. This particular event may have been a Type II supernova, the core collapse of a massive star. But what if the progenitor star was not massive in a conventional sense? Could it have been a star of relatively low mass that, through a complex dance with a companion in a binary system, gained extra mass and was pushed over the edge into instability? Such a star might have lived a quieter, less luminous life right up until its sudden, violent end, making it inherently harder to spot in pre-explosion images. The most exotic explanation, however, ventures into entirely new physics. Could this supernova have been triggered by a mechanism we have not yet considered? One speculative idea involves a process called a failed supernova, where a massive star collapses directly into a black hole without the traditional, brilliant explosion. But this event was brilliant, so perhaps it was the opposite, a star not quite massive enough to undergo core collapse on its own, but ignited by an internal chain reaction or an external shockwave we do not yet understand. This transient supernova with no past is a ghost in the cosmic record. It tells us that our maps of stellar life cycles, while robust, still have blank spaces. Some stars may march toward their doom in shadows so deep we cannot see them until the moment they tear themselves apart, reminding us that the universe still holds secrets about the final moments of its most massive citizens. A supernova without a past is a solitary mystery, but the very atmosphere of the Leo cluster is etched with patterns of ancient weather. The X-ray glow of its million-degree gas is not a uniform haze. Cutting through it are sharp, defined boundaries, edges where the temperature plummets by tens of millions of degrees over a shockingly short distance. Astronomers call these structures cold fronts. The name is a perfect analogy. On Earth, a weather front is the boundary between a mass of cold air and a mass of warm air. In the Leo cluster, these are fronts between oceans of unimaginably hot plasma, and they are not gentle gradients. They are razor-sharp, like the surface of a bubble submerged in a boiling sea. The existence of such crisp edges in a superheated, turbulent environment is a profound thermodynamic puzzle. Everything we know about physics says these fronts should not last. In a gas this hot, particles are moving at tremendous speeds, constantly colliding and sharing energy. This process, called thermal conduction, should act like a cosmic blender, smoothing out temperature differences in a relatively short time, perhaps a few 100 million years. The cold fronts we observe, however, are billions of years old. They have survived across cosmic epochs, maintaining their stark definition against all odds. It is as if you drew a line in the sand at the ocean's edge and returned 1,000 years later to find it perfectly intact, untouched by the waves, wind, and tides. So what is protecting these ancient scars? The leading explanation is magnetism. The intracluster medium is not just hot gas, it is a plasma threaded with faint but pervasive magnetic fields. These fields, though incredibly weak by earthly standards, can profoundly influence the motion of charged particles. The theory is that these cold fronts are not just temperature boundaries, but also magnetic boundaries. The magnetic field lines may be draped along the surface of the front, forming a kind of insulating blanket. This magnetic sheath would suppress the cross-boundary collisions of particles, effectively putting up a barrier that prevents the hot particles from rushing in to warm the cold region and the cold particles from leaking out. The front becomes a stable, magnetically insulated structure, a cosmic version of a thermos wall, keeping its contents separate from the surrounding heat. But this only deepens the mystery. Where did these organized magnetic structures come from? Their likely origin is violence. Cold fronts are believed to be the fossilized remnants of colossal mergers, the sloshing edges of vast pools of gas set in motion when subclusters collided. During that unimaginable collision, the turbulent motions could have amplified and stretched the cluster's primordial magnetic fields, weaving them into the sharp interfaces we see today. The front is therefore a layered relic. It is a temperature map of an ancient impact and a magnetic fossil of the turbulence that impact created. The fact that it endures tells us that the cluster's atmosphere has a memory and that magnetism can sculpt and preserve structures in places we once thought were governed only by chaotic heat. These cold fronts are more than just curiosities. They are natural laboratories for studying plasma physics on a scale no experiment on Earth could ever replicate. By deciphering how they survive, we are learning that even in the most energetic places in the universe, there can be pockets of enduring order, sharp lines drawn in a sea of fire that refuse to fade. The cold fronts are scars from ancient collisions, but one system in the Leo cluster is a portrait of a crash happening in slow motion. Deep within this crowded city of galaxies, astronomers found a cosmic traffic jam of unimaginable scale. Not two, but three supermassive black holes are spiraling toward a catastrophic merger, the result of a triple galaxy collision that has left a single, chaotic system in its wake. This is a dynamical nightmare, a gravitational three-body problem playing out with the most destructive objects in the universe. Normally, when two galaxies merge, their central black holes will eventually sink to the new core and coalesce. Adding a third black hole into that dance throws all predictability into chaos. The interactions become fantastically complex, a game of gravitational pinball where one black hole can be violently ejected, flung out into intergalactic space as a rogue monster while the other two couple together. Or all three can engage in a frantic, unstable waltz, exchanging energy and momentum in ways that defy simple calculation. The mere existence of this system, caught in this transient state, tells us that the core of the Leo cluster was once an even more crowded and violent place than we imagined, a cosmic demolition derby where triple encounters were possible. But the true legacy of this trio will be written in ripples in spacetime itself. When two supermassive black holes finally merge, they unleash a torrent of gravitational waves, ripples in the fabric of the universe predicted by Einstein. A binary merger produces a characteristic signal, a rising chirp. A triple merger, however, would create a gravitational wave signature of bewildering complexity. The signal would not be a clean chirp. It would be a stuttering, chaotic cacophony of frequencies as the orbits of the three bodies perturb each other, shifting the frequency and amplitude of the waves in unpredictable jumps and dips. Detecting such a signal would be a triumph for observatories like the Future Laser Interferometer Space Antenna, LISA, and it would provide a direct test of gravity under the most extreme conditions imaginable. This system is a ticking bomb, a snapshot of a process that will culminate in an event that will shake the cosmos itself. We are witnessing the prelude to a symphony of space-time composed for three black holes, and we are only just learning how to listen. The gravitational cacophony of merging black holes will shake the very fabric of space-time, but a far quieter signal whispers from the dust of the cluster. Within the spiral arms of certain Leo cluster galaxies, a faint, anomalous microwave glow defies every conventional explanation. This is not the sharp radio blast of a synchrotron jet, nor the predictable thermal warmth of starlight-heated dust. It is a persistent, mysterious hum in a frequency range where the cosmos should be relatively silent. The source appears to be cosmic dust itself, the tiny, frigid grains that drift in interstellar space, the same material that dims starlight and forms the seeds of future planets. Yet something is causing these minuscule particles to emit microwaves in a way our physics cannot yet fully account for. Think of it like this. You walk into a dark room expecting to feel only the gentle warmth of a radiator. Instead, you hear a faint, high-pitched whine coming from the cold stone floor. The radiator explains the heat, but the sound is coming from somewhere else entirely, generated by a process you cannot see. In these galaxies, astronomers have accounted for all the usual sources of microwave emission. What remains is this unexplained whisper, a background signal that stubbornly clings to regions rich in complex dust. Two leading theories attempt to give this whisper a voice, and both venture into the realm of the extraordinarily small. The first points to spinning nano-dust. Imagine the tiniest specks of carbon or silicate, molecules barely larger than a few atoms across, floating in the harsh radiation fields between stars. When an ultraviolet photon from a nearby star strikes one of these nanoparticles, it can set it spinning at dizzying rates, billions of revolutions per second. A spinning electric dipole, no matter how tiny, emits radiation. The collective hum from trillions upon trillions of these frenetically spinning grains could, in theory, produce the very microwave signal we detect. It would be a cosmic chorus sung by the smallest members of the dust family. The second theory delves into even stranger physics, involving magnetism at the molecular level. Some dust grains may contain atoms with unpaired electrons, making them magnetic. As these magnetic grains tumble through space, their fluctuating magnetic fields could generate radiation directly through a process called magnetic dipole emission. This is a fundamentally different mechanism from the spinning charge idea, one that ties the anomalous glow to the hidden magnetic personalities of the dust itself. The challenge is that both ideas push our understanding of solid-state physics in extreme environments. We must imagine processes on a scale far below what we can replicate in any laboratory, playing out in the freezing vacuum of interstellar space. The presence of this anomalous emission in the Leo cluster is particularly telling. The cluster environment, with its intense radiation fields and turbulent gas, could be the perfect laboratory to excite these exotic processes. Perhaps the anomalous microwave glow is a signature of a special, battered population of dust grains, ones that have been processed by supernova shocks or stripped from galaxies and forged anew in the intracluster medium. Its very existence suggests that the humble dust grain, often an afterthought in the grand drama of galaxies, may harbor a complex inner life and a way of speaking to us we are only beginning to hear. This faint microwave whisper is a reminder that even the most common ingredients of the cosmos can hold profound and quiet secrets. That faint microwave whisper is a signal from the smallest scales, but the cluster also holds the ghost of a structure that was once unimaginably dense. Winding through the stellar fog between the galaxies is a river of light so faint it was almost mist. This is a stellar stream, a long, graceful arc of orphaned stars tracing a path through the darkness. Unlike the broad, diffuse glow of intracluster light, this stream is a coherent thread, a single strand pulled from a cosmic tapestry. Its origin is a tale of destruction. Astronomers believe this stream is all that remains of a globular cluster that ventured too close to the gravitational heart of the Leo cluster. A globular cluster is a spherical swarm of up to 1 million ancient stars bound together in a tight, dense ball. Think of it as a single, glittering diamond. The tidal forces near a massive galaxy or in the chaotic core of the cluster itself act like a hammer. They can pull that diamond apart, stretching it into a long, shimmering strand that slowly disperses its stars into the void. This stream is the diamond unraveled. But the mystery lies not in its destruction, but in its composition. When scientists analyzed the starlight from this faint river, they found a chemical signature that did not fit. Globular clusters in our own Milky Way are famously ancient and metal-poor. The term metals in astronomy means any element heavier than hydrogen and helium. These heavier elements are forged in stars and scattered by supernova. Old globular clusters formed from pristine gas before many stars had lived and died, so their stars contain only trace amounts of these metals. The stars in this Leo cluster stream, however, show a subtly higher metallicity. They are not rich in metals by any means, but they are not as impoverished as they should be. This small difference is a giant clue. It suggests this was not a typical globular cluster. One possibility is that it was the core of something much larger. Perhaps this stream is the final remnant of a dwarf galaxy that was almost completely devoured. Dwarf galaxies, while still old, often have more complex star formation histories than globular clusters. They can experience multiple generations of stars, with later generations enriching the gas with more metals. If a dwarf galaxy was stripped down to its dense, star-packed nucleus, that nucleus could masquerade as a globular cluster until the final tidal forces stretched it into this stream. The higher metallicity would be a fossil memory of its more complex galactic past. Another, more intriguing idea is that this globular cluster itself had a unique birthplace. It might have formed not in the pristine halo of a galaxy, but within the turbulent, metal-enriched disk of a massive spiral galaxy during an early, vigorous period of star formation. Later, a galactic collision could have ripped it free, ejecting it into intergalactic space where it wandered for eons before finally being torn apart by the cluster's gravity. Its chemical abundance would be a birth certificate, proving it was born in a richer, more processed environment than the ancient halo clusters we know best. This faint river of stars, then, is more than a scar. It is a lineage test. Its starlight carries the nuclear history of its origin, a story written in the subtle blend of elements within each sun. As we trace its graceful arc across the void, we are not just following the path of destruction. We are reading the biography of a structure that no longer exists, a biography that challenges our simple categories and reminds us that every stream of light in the cosmos has a story to tell, if only we know how to listen. The chemical story told by a stellar stream is written in starlight, but the Leo cluster's final mystery is written in invisible lines of force. Across millions of light-years of seemingly empty space, the cluster's magnetic fields are not randomly oriented. Recent observations reveal a startling and puzzling coherence. These fields show a subtle but detectable degree of alignment over vast intergalactic distances. This is not the tangled magnetic web of a single galaxy. This is order on a scale that dwarfs any single structure, a whisper of organization in the most diffuse regions of the cosmos. Generating such large-scale alignment is a profound challenge. Magnetic fields are not free-floating entities. They are frozen into the hot plasma of the intracluster medium, their lines stretched and twisted by every motion of that gas. In a turbulent environment shaped by billion-year-old mergers and constant agitation, you would expect these fields to be a chaotic snarl, with directions canceling each other out into randomness. The suggestion of alignment is like finding that after a hurricane has passed through a forest, all the fallen trees are pointing in roughly the same direction. Something must have combed them into order. One compelling theory points to the breath of giants. For billions of years, the most massive galaxies in the cluster have been exhaling. Their supermassive black holes in their red geyser phase and their collective supernova winds have been blowing colossal outflows of magnetized plasma into the intergalactic void. Imagine 100 bellows scattered around a giant workshop, all pointed in roughly the same direction and blowing for eons. Over time, their combined breath could slowly impose a preferred direction on the cluster's magnetic environment, weaving the separate threads into a looser but coherent tapestry. The fields are not perfectly aligned, but they bear the memory of that persistent directional forcing. An alternative and equally dramatic explanation looks outward beyond the cluster itself. The Leo cluster is not stationary. It is falling with immense gravity toward an even larger concentration of mass in the cosmic web, a region known as the Great Attractor. As the entire cluster plows through the tenuous intergalactic medium, it may experience a form of cosmic ram pressure. This motion could create a bow shock at its leading edge, a vast wall of compressed and ordered magnetic fields. Turbulence behind this shock might then spread that ordered orientation throughout the cluster's interior, like a wake smoothing out behind a ship. In this view, the magnetic alignment is a compass, pointing the way the cluster is moving on its epic journey through the universe. The implications of either story are far-reaching. Magnetic fields, though weak, play a crucial role in the life of a cluster. They govern the transport of heat, they confine cosmic rays, and they influence the stability of gas clouds that could form stars. A large-scale aligned field could channel energy and particles along preferred routes, creating hidden highways that shape the cluster's evolution in ways we are only beginning to map. This final phenomenon ties the cluster together not with gravity, but with invisible threads of force. It suggests that the history of the Leo cluster is recorded not only in its stars and its scars, but in the subtle polarization of light traveling through its depths, a faint signature of order etched across a sea of ancient chaos. These magnetic highways could be conduits for the universe's most energetic particles. Cosmic rays, atomic nuclei accelerated to near light speed, do not travel in straight lines. They spiral along magnetic field lines like beads on a wire. A large-scale, aligned field in the Leo cluster would act as a galactic-scale channel, guiding these relativistic particles over immense distances and concentrating their energy along specific paths. This could explain mysterious hotspots of gamma-ray emission or influence where and how gas cools within the cluster, subtly directing its evolution. The fields themselves, however, need an origin story. One profound possibility is that we are seeing the amplified ghost of creation. Theorists propose that the alignment could stem from primordial seed fields, infinitesimally weak magnetic imprints generated in the first moments after the Big Bang. Throughout cosmic history, as gas collapsed to form the cluster, these seed fields would have been stretched, twisted, and amplified by the turbulent motions of plasma, like a tiny scribble enlarged to cover a vast canvas. The resulting pattern might still retain a faint memory of that initial direction, a fossil orientation preserved for over 13 billion years. An alternative, more dynamic origin lies in the cluster's own violent adolescence. During the epoch of maximum galaxy formation, the young, fierce stars and voracious black holes of the Leo cluster's founding galaxies would have blasted out winds of magnetized plasma. If these galactic outflows were coordinated by the large-scale flow of gas along the cosmic web filaments that built the cluster, their combined magnetic breath could have woven a coherent pattern into the intracluster medium from the very beginning, a template that later mergers stirred but never fully erased. Distinguishing between these cosmic blueprints requires a new kind of vision. The key lies in mapping the magnetic field structure with exquisite detail, far beyond what current telescopes can provide. The next generation of radio observatories, like the Square Kilometre Array, will act as cosmic polarimeters. They will not just see the cluster, they will read the subtle polarization, the directional twist, imprinted on radio waves as they pass through this magnetized plasma. By analyzing how this polarization changes across the cluster's vast face, astronomers could trace the field lines as clearly as iron filings reveal the shape of a magnet's field. We could see if the alignment follows the gentle contours of ancient outflows, the sharp edges of merger shocks, or the radial patterns of infall from the cosmic web. Each configuration tells a different story of the cluster's birth and growth. This invisible architecture, once fully charted, would reveal more than just a magnetic curiosity. It would show us the hidden currents that shape the cluster's climate, guiding its energetic particles and perhaps even orchestrating the slow dance of its gas. The final mystery of the Leo cluster, then, may be written in lines of force we are only now learning to see, a signature of order that has endured since the dawn of time, silently guiding the chaos within this city of galaxies. The magnetic whispers and stellar ghosts we have traced are not isolated curiosities. They form a single, interconnected tapestry of mystery woven across the Leo cluster, a testament to the universe's boundless capacity to defy our expectations. From the staggering emptiness of the Fornax void to the impossible density of an ultra-compact dwarf, from a black hole that should not exist to a galaxy made almost entirely of shadow, each phenomenon challenges a different pillar of our understanding. These are not mere gaps in knowledge, they are signposts pointing toward new physics, new histories, and new stories about how the cosmos builds itself. Every unexplained radio relic, every chemical anomaly in the hot gas, every orphaned star in a faint stream is a question that drives observation, theory, and invention forward, pushing our telescopes and our minds to their very limits. This distant city of galaxies, floating hundreds of millions of light years away, is more than a collection of stars. It is a cosmic laboratory, a grand puzzle box whose pieces are slowly being turned by the relentless curiosity of science. So tell us, as we leave this cluster of secrets behind, which of its 25 mysteries captured your imagination the most? Was it the phantom galaxy Dragonfly 44, the screaming repeater, or the ancient scars of the cold fronts? Let us know in the comments below, and if you crave more journeys to the edge of understanding, be sure to subscribe. The universe is vast, and its greatest secrets are still waiting to be